we have variables x1, x2, all the way to xn. Each one of them is between L and U. L is strictly positive and U is strictly greater than L. So given those box constraints, we are interested in maximizing the arithmetic mean of those variables divided by the harmonic mean. The ratio of the arithmetic mean to the harmonic mean is 1 over n squared, and then we have the product. In one bracket, we have the sum of the x's, like here, and in the other, we have the sum of the reciprocals. N is given, okay, so we'll focus on this product here. To gain insight into the problem, let's do the case of small n equal to, when we multiply x1 by 1 over x1, that's 1, x2 by 1 over x2, that's another one, so we get 2, and then we get x1 over x2 plus x2 over x1. So if x1 over x2 is alpha, then here we are maximizing alpha plus 1 over alpha plus 2. And alpha, which is x1 over x2, the minimum possible value is when x1 is L and x2 is U, and the maximum possible value is when x1 is U and x2 is L. Now, the derivative of this function to be maximized is 1 minus 1 over alpha squared, and this first derivative is 0 at alpha equal to 1, and it is, if alpha is less than 1, then 1 over alpha is greater than 1, and 1 minus 1 over alpha squared will be negative. If alpha is greater than 1, then 1 minus 1 over alpha squared will be positive. So the sign of the first derivative will be negative, and then it's 0 exactly when alpha is equal to 1, then it is positive. So this function that we have is decreasing, and then there is a minimum at alpha equal to 1, and then it increases. Note that our problem is a maximization problem. So we are interested in the maximum of psi 2. In this case, the maximum will occur at the boundaries. So alpha is L over U or U over L. And this is obtained by setting x1 equal to L and x2 equal to U, or vice versa. This will indicate that, most likely the solution will be a boundary solution in which the variables will take the values L or U. Suppose that we have this problem of maximizing this sum of the y's plus some non-negative constant C1 and the sum of the reciprocals plus another non-negative constant C2. And the y's here are like our x's, so they live between the strictly positive L and big U. So we are interested in this. Again, it looks very much like our problem. So we have a sum, but then we just have here a factor, which is, so we add a non-negative constant, and here we add another non-negative constant. Now, if you focus on this product and focus on its dependence on one of the y's, let's say y sub m. So what we can do is separate y m from this summation. So now it is a sum from 1 to m minus 1, and then we have C1, which is here, and then ym. Also, we can separate 1 over ym from this sum of reciprocals. Now, differentiate h with respect to ym. We are interested in investigating how h varies as we change ym. The derivative of the product, so the derivative of the first bracket, that's 1, and then we multiply, so we have 1 times the second bracket, and then we take the first bracket and differentiate the second one with respect to ym. Those guys do not depend on ym, and the derivative is -1 over ym squared. If we do this multiplication, we get -1 over ym squared, and then the sum, I from 1 to m minus 1 yi. Then we get minus c1 over ym squared, and then we have -1 over ym squared times ym, that's -1 over ym, and this term will cancel with this term here. The survivors are the sum of the reciprocals, j from 1 to m minus 1, then we have the constant c2, then we have -1 over ym squared, and we have these two terms, the sum of the y's, I from 1 to m minus 1, and c1. That's the first derivative. Take the second derivative with respect to ym. Ym is not here, this is a constant, and now we have minus this quantity here, which is considered constant, over ym squared. So the second derivative will be 2 over ym cubed, 2 over ym cubed, multiplied by this bracket here, which is the non-negative constant c1 plus the sum of the y's from 1 to m minus 1. Now, this second derivative, because the y's are strictly positive, in fact, they are greater than or equal to L, which is strictly positive, and because C is non-negative, regardless of the values of those y's or what C1 is, the second derivative is strictly positive. So assign any value to those y's so long as we obey the box constraints and we choose the constant C1 to be non-negative. The second derivative of h with respect to ym is strictly positive. So this function is convex. It is a strictly convex function. Now, ym is a variable and it lives between L and U. So we can write down ym as a convex combination of L and U. So there exists a lambda between 0 and 1 such that ym is lambda times L plus 1 minus lambda times U. And, we can, given ym, we can find lambda, right? So ym is equal to U minus lambda U minus L. Okay, and so lambda U minus L is equal to U minus ym. And so if you know ym, then lambda is U minus ym over U minus L. The important thing is that there is a lambda between 0 and 1 such that ym is a convex combination of L and U. Now, the value of the function at ym is the value of the function at this convex combination, lambda L plus 1 minus lambda U, where lambda, takes a value that depends on ym. Now we have shown that the function is a convex function. Because of convexity, the function evaluated at lambda L plus 1 minus lambda U is less than or equal to lambda H of L plus 1 minus lambda H of U. Now, this H of L is less than or equal to the maximum of the two quantities H of L and H of U. And this H of U is also less than the maximum of these two quantities H of L and H of U. So we can upper bound H of L and H of U by the maximum of the two terms, take that as a common factor, and then we are left with lambda plus 1 minus lambda, which is 1. So H of Ym is less than or equal to the maximum of H of L and H of U. If we are interested in maximizing such a quantity, then for variable Ym, H of Ym is less than or equal to H evaluated at the endpoints L and U. So to maximize, and regardless of the other choices for the y's, we should take Ym to either L or U. The reason for this is that convexity is proved regardless of what those have. We always have H being a convex function, and so it will achieve a maximum at the endpoints L or U. So if we go back to our problem, we have psi n, and it is the sum of the x's times the sum of the reciprocals. So think about xn. So isolate xn from the sum and from the sum of the reciprocals. And this looks like the problem that we have just investigated with the constants being equal to 0. And now we know the story. If we think of this as a function of xn, then it's a convex function regardless of the other x's, and it is maximized with xn equal to L or xn equal to U. So now what you can do is that you put xn equal to L or equal to U. This is to be investigated later. So let's suppose that we will put xn equal to big C, and big C can be L or U. Note that also our argument here turned out to be, independent of C1 and C2. So whether C is L or U, our argument will work. Xn will be equal to C, which is L or U. And now to maximize this with respect to x of n minus 1, we can isolate it. And again, the argument above tells us, regardless of other choices, this is the most important thing, we can maximize regardless of C. So regardless of whether xn will be L or U, and regardless of the other x's, xn minus 1, should be set to L or U. Again, because this is a convex function of xn minus 1, regardless of the value of C, and x1 all the way to xn minus 2. And because it's a convex function, then it attains its maximum by pushing xn minus 1 to either the lower bound L or the upper bound, which is U. Now we will set this guy equal to L or U. Then we can isolate xn minus 2 from here and there, and so the argument is repeated. Okay. So this is a demonstration that the variables will be L or U. So the maximum, to maximize the arithmetic mean to the harmonic mean, to maximize this ratio with the box constraints that every x is between the strictly positive L and u, which is larger than L, then we should use, x's that are either L or u. And it's sort of, we need half of them to be L and half of them to be u. So, if you solve for the case of n equals 2, as we did, then like one of them must be L and one must be u. So it is like, this gives a hint that we need about half of the variables to be set to the lower bound L and the other half to the upper bound, which is u. And let's basically verify this. Suppose that n is even, and psi n is maximized when n over 2 variables are L and n over 2 variables are u. Okay, so for example, we know already this, that if n is equal to 2, psi 2 is maximized when one variable is equal to L and the other is equal to u. Now we ask about this, that how can we maximize psi n plus 1? So we have one more variable. So the extra variable, we know that its maximum should be L or U. So will it matter? So can we set it to L or to U, or we get the same objective? Let's verify this. So if we take xn plus 1 to be equal to L, so we started with n over 2 variables that are equal to L. Note that n is even, and so n over 2 is integer. So we started with n over 2 variables that are equal to L. Now, if we take this extra variable to be L, then we have n over 2 plus 1 guys that are equal to L and n over 2 guys that are equal to U. So the sum of the variables will be n over 2 plus 1 all times L plus n over 2 times U. And the sum of the reciprocals will be, so we have n over 2 plus 1 L plus n over 2 U, and the reciprocals, we have n over 2 plus 1 divided by L plus n over 2 divided by U. Now, when we multiply, then these two terms will give n over 2 plus 1 all squared. L will cancel with L. When we multiply these two terms, it will be n over 2 squared. U will cancel with this U in the denominator. And then we will have the cross term. So we'll have n over 2 times n over 2 plus 1. Okay, and in one case we get L over U, in the other case we get U over L. So this is what we get. Now, if we choose x of n plus 1 to be equal to U, we actually get the same objective, which means that if the psi n plus 1, given that n is even, is maximized, we have the choice to make this extra variable xn plus 1 L or U. In both cases, we will achieve the same objective. So when this happens, then we will have the variables. Their number is odd when n is even. N plus 1 will be odd. And basically, if we make this a choice, then n, then if we make this a choice, then n over 2 plus 1 will take the value L, and n over 2 will take the value U, or vice versa. Now, what if n is odd? If n is odd, let's take that, about half of the variables will be L and the others U. So we can take n minus 1 over 2 variables to be L and n. So this should be, so the minus here. So if we have n minus 1 variables that are L, then we have n plus 1 variables that are equal to U. And if we have n plus 1 variables that are equal to L, then we have n minus 1 variables that are equal to U. We can actually investigate the fourth case. So suppose that you have one extra variable that is set to U. Okay. Then what will happen that if you put xn plus 1 equal to U? So now you are increasing the difference between the number of variables equal to u and those equal to L. In this case, the number of variables equal to u will be n plus 1 over 2 plus 1, so that's n plus 3 over 2 times u, and the number of variables equal to L will be equal to that quantity. And here is the bracket, the sum of the reciprocals, and we will achieve this objective. But what if we take xn plus 1 to be equal to L? In this case, we will make the number of variables equal to L and u equal, because we started with n minus 1 variables equal to L, n minus 1 over 2 variables equal to L, and n plus 1 over 2 variables equal to u. Now the extra variable xn plus 1, when n is odd, we will set it to L. So now we have n plus 1 over 2 variables that are equal to L, and n plus 1 over 2 variables that are equal to u. Now you will achieve another objective. Now these two guys are not the same. So which one is better? So we have basically, we started with an n equal, an odd n case. Now we have one extra, an odd n case, and the number of variables equal to u is one more than the number of variables equal to L. Now, if we make the new variable equal to L, which means that we equalize, we will get this psi n plus 1. And if we further increase the number of variables equal to u, we get this one. Let's take the difference. So if we take the difference between the two guys, we will get, after some simplification, we will get the difference to be L over u plus u over L minus 2. That's the difference between these two values, this minus that. Now we can make actually a judgment regarding this quantity. So this quantity is indeed greater than 0, because L over u plus u over L by the arithmetic mean geometric mean inequality is greater than or equal to double the square root of the product, and the product is equal to 1. So L over u plus u over L is greater than or equal to 2. Moreover, we have equality if and only if L is equal to u, but u is strictly larger than L. Then this quantity here is strictly greater than 2, or this bracket minus 2 is strictly positive, which means that the way to go here for maximization is actually, if you start with n minus 1 over 2 variables that are L and n plus 1 over 2 variables that are u, is actually to increase the number of variables equal to L, so that now we have n plus 1 over 2 variables equal to L and n plus 1 over 2 variables equal to u. If we start with n plus 1 over 2 variables equal to L and n minus 1 variables equal to u, we will discover that actually the best here is to choose xn plus 1 equal to u, again to equalize. So it will always be the rule that we achieve the maximum by having almost half the variables equal to L and the other half equal to u. Okay, so this is the summary. So if n is even, n over 2 variables are set to L, n over 2 variables are set to u, and we can basically get the value of the objective function, and it is equal to this. If n is odd, then n minus 1 over 2 variables are set to L, and in that case, n plus 1 variables are set to u, or vice versa. And again, we can basically compute the sum and the sum of the reciprocals, and this will be the value of the maximum value of psi n. Our quantity of interest is the ratio of the arithmetic mean to the geometric mean. And so basically the ratio is this psi n divided by n squared. So we can take those guys and divide by n squared, and our final result will be, if we have n variables living between L and u, and L is strictly greater than 0, then if n is even, this is the maximum possible value of the ratio of the arithmetic mean to the harmonic mean, achievable when half the x's are equal to L and the other half is equal to u. If n is odd, then the maximum of the ratio of the arithmetic mean to the harmonic mean will be given by this quantity. And now the maximum is achievable. We will have one extra variable equal to L or one extra variable equal to U.